Now we are going on to chapter 3, which is on derivatives. We will talk about concepts and derive the definition, or talk about the definition. 3.1, first is on tangent lines and derivatives at a point, and we will define the definition of derivative. So first, let's talk about our goal right now. So we're going to look at tangent lines, what those are. Our goal is to find the tangent line to a curve at a point. Like, what does that mean? So if we take a curve, so take a curve. So I'm just going to draw it. This is what we do for generic curves, something like that. And then we want to describe what we mean by a tangent line. So if you take a point on the line like that, we know the idea is we have a line that comes in and just touches at one point. Okay, so how do we get that? How do we define that line? That's the question. Okay, so if you have a point P, we want to define what that is. So our question is, I'm going to paste this in here. So here's our question. It fits close enough, I guess. Okay. That'll work. Okay, so how would we describe, sorry about my handwriting there, how would we describe the line mathematically? Okay, we can talk about it, a line that just touches a curve in one point. This is our curve C. We can talk about that in words, but you got to have a way to describe it with mathematical terms. And so the other way of asking a question is, what does it mean to be tangent line, to be a tangent line? And again, we can say it, but we have to define it mathematically. So that's what we're going to do in this chapter, section, whatever. So let's draw another curve. This one I'll do a little differently just for sake of discussion. Let's see, it goes like this. And so we're going to call that now f of x. So you have some function, and it is like a function, so it doesn't like curve back on itself or anything. So what we want to look at then is this idea. Let's just go back to this color. So if you have a point, say P here, then we can look at another point on the line up here, Q. We already did this once a while ago. So that's Q. And then we can look at the change in x over change in y. Zoom in a little bit. So this would be your delta x, and this is your delta y. Now, if we go through those 2 points, P to Q, then you end up with this secant line. Pretty close. Okay, so that's the secant line, L. So L can be described like this. Okay, so like the slope and stuff. So let's talk about L. So L we know can be written as y equals mx plus b, where this would go down and touch the y-axis, and that's your b. Then you have the slope is your rise over run. Okay, so we'll write all that stuff down. We know that your slope m is equal to your delta y over your delta x. That's how it's defined. Y2 minus y1 over x2 minus x1. And we know that's equal to the slope of the line. Okay, so what we're going to look at then is how do you start defining a line that's the tangent line. So we know the tangent line is going to look more like this. Okay, that doesn't go straight like this, does it? Okay, so it goes like that. It's tangent. I'm not drawing it very well. Okay, there we go, a little better. That's your tangent line. So I'm going to define this pretty carefully, actually. Here, let me go ahead and put in your points P. Then this would be, both of these are of x how do I define that? Yeah, x1, y1. This would be x2, y2. So this is how it's defined. This is more of like the more careful derivation, I guess you could say. So consider the point on the curve. So it's like the curve itself, you could call it like curve C or something. And then the function defines the curve, is the way how you describe it. So to the point on the curve, and I'll be drawing a picture below to describe all this stuff. P, and it's going to be A, and then your function value, your y value is your f of A. So we're going to stay away from your y's right now, just to make it better. And another point, Q, which will be x f of x. Okay. Now, the way I wrote that, it's I don't have to define it. I don't want to get too crazy about this, but we're kind of assuming that the a is fixed and then that the x is arbitrary, or like a variable. It's arbitrary. So your x is going to be able to move and get closer to your a, like we've done with limits. Okay, then what we have is the line PQ is called the secant line. Then we're going to let LPQ be the secant line. This will make more sense when I draw the picture. Through PQ. M is the slope of LPQ. MA is the slope of the tangent line. L at A P of A. Okay, so let's take a look at what this is. We have kind of this picture. We have the, so I'm going to describe all that stuff now. So we have M PQ. The slope of PQ is f of x minus f of a all over x minus a. Okay, and then let's draw in our our curve. So we have this graph like this. Do this again. And then we have some curve. Let's see if I can draw it okay. Don't like that one. Let's try another one. Something like that. Actually, I needed to be a little more. Okay. Third time's a charm there, yes. So we have a point here, P, and another point here, Q. And you first have that secant line like that. And then what happens, and this is something we did talk about before, what we're going to do is we're going to say this. We're going to suppose x approaches A, but x never equals A. So what we get then is this idea, is you start getting these You get that. Oops, that's kind of tangents. You get that graph. Let's just zoom in on that a little bit. So you get that one, and then you get the next one, and eventually you get that tangent line for the slope. You have a point and a slope, then you can always define the curve. So what you get is multiple points going like this, coming closer and closer to the actual value. And then you end up eventually getting that tangent. And that's close, but not real accurate. But you get that tangent right there. So what you get then is, oh, and then let's see, P is up here. Let me clean this up a little bit because I do this partial. I want to put in up here the, didn't turn out too well, did it? This is your function value up here. That's your f of a. And then, okay, that's good enough. So the slope, so therefore, your slope of the tangent line must equal f of x minus f of a. I'm sorry. Give me a second here. Put this over here and erase that. Okay. We want to approach that value. So down here, this is my a value, and then I'm saying I'm going to start off here with x. Well, you're going to like that's your x1. Then you're going to get closer and closer to closer, x1, x2, x3, etc. Like that. You're getting all the way in like that, approaching a. Now it can come from the other side. I mean, we could have x values over here, and then your secant line would be like that, and then you get it to be eventually that slope. So we can approach from either side, but we'll just keep it this side right now. So that's a limit, isn't it? That's the limit as x approaches a. So the slope of the tangent line we can say is, and actually define it as, the limit of f of x minus f of a as x approaches a. Okay, so that's actually, by definition, going to be the slope of the tangent line. Okay, because that's exactly what we are doing. So you get those graphs that are approaching closer and closer and closer. Now, we're going to define a few more things. Let me grab the book's picture on my notes, which is down here. And take a second to look at that. That's a little better drawing how I drew it before. You can see that these slopes, start here, and then they start getting closer and closer and closer as you have points getting closer and closer to A. Same thing I wrote there. I wanted to grab this and talk about this. This is right from the book, because we're going to be able to want to define another way to write it. Okay, so using this notation, so take a moment to pause and study this thing. What we're doing now is we're saying this is the limiting value, or the value we're heading towards, x naught, or x sub 0, we say x naught, right? And then you're saying x naught plus a little bit, plus h. So h is basically some positive small number like that. And so we're saying x naught plus h. And we're going to now let h approach 0. So it's going to come in like this then, because this value here is getting smaller and smaller and smaller. So he starts going like this, closer and closer and closer to here. And then this, oops, not that one. This secant line then is getting closer and closer and closer to eventually being that tangent line. Okay, so that's what we want to do. That's our goal. So you end up having those different lines. You end up having like this one, goes on both sides. No, it didn't work out too well. And this one, and then eventually you get the one in question, which is that. That's the tangent line. So that's that. That's your justification of why we're doing this, but that's going to be the definition of slope of a line, slope of a tangent line to a curve. So let me write up the other case. We're going to say, from the description above, I'm going to write this. I'm going to say let h equal x minus a. Then, if you solve for x is equal to h plus a, which is a plus h. You can just commute that. And then we can write the slope of the tangent line at a is the limit of f of a plus h minus f of a all over h as h approaches 0. So the only difference is my a is now going to be x naught instead of in their definition down here. So you just need to see how that's exactly the same thing, and then your a is just x naught. Okay, so that is basically the definition of the slope of the tangent line to a curve. Okay,